Good morning everyone. So today we are going to talk about Bessel equation and Bessel functions. So differential equation of the form x square y double dash plus xy dash plus x square minus p square y is equal to 0 is said to be Bessel equation and its solutions are called Bessel functions. Remember that here p is a non-negative constant, which means p is greater than 0. In case of Legendre polynomial or Legendre equation, p used to be a non-negative integer. So remember the difference. Now it can be easily observed that x is equal to 0 is a regular singular point. Hence, there exists Frobenius series solution. We need to see, does there exist one Frobenius series solution about x is equal to 0 or two Frobenius series solution. Now Frobenius series solution can easily be computed. I have given the details here. So the first step is to find the initial equation or the roots of the initial equation. So if you compute it, you will observe that m are p and minus p. And the recurrence relation would look like an plus 2 is equal to minus an by m plus n plus p by 2, m plus n minus p by 2. Yes. If I substitute m is equal to p or minus p, you can observe here that I cannot compute a1 from this recurrence relation because n starts from 0. So I can compute a2, but a1 is missing. So it means that to proceed further, I have to compute a1 first. So first we will find the solution for m is equal to p, and later on we will find the solution for m is equal to minus p. So for m is equal to p, this is my recurrence relation, and if I have to find the value of a1, I equate the coefficient of x raised to the power m plus 1. That gives me a1 is equal to 0 for m is equal to p. Simple observations are there. Please do try all of these things by yourself. Now in the recurrence relation, if you compute a2, a4 and so on, since a1, a3, a5 all are 0, it's a easy observation. If you see a4, then a4 is a0 by 2.4, 2p plus 2, 2p plus 4. It means that if you find a2n, so a0 by 2, 4, 6, it goes till 2n, then 2p plus 2, 2p plus 4, it goes to 2p plus 2n. It means I can write a2n as follows. It is multiplied by a0. Yes. Now from here what you can observe that 2.4.2n can be written as, you can take 2 common from all the terms and there are n terms, so 2 raised to the power n would come out to be common and the remaining terms would be 1.2 till n, which is n factorial. Similarly, the second term is 2p plus 2, 2p plus 4 and so on, and 2p plus 2n. If you take 2 common from all the terms, 2 raised to the power n would come out to be common and the remaining terms would be p plus 1, p plus 2 and p plus n. Now if I multiply and divide by p factorial, then it becomes 2 raised to the power n p plus n factorial divided by p factorial. Yes. So this becomes p plus n factorial and divided by p factorial. Now substitute all these values. So a2n becomes minus 1 raised to the power n a naught, 2 raised to the power n factorial, 2 raised to the power n, and then p plus n factorial, and p factorial goes in the numerator. So it means this is my one solution about x is equal to 0. Now Bessel functions have their special significance, which means if I substitute a naught is equal to 1 by 2 raised to the power p factorial, so a fixed constant which depends on p, then this y of x is known as or is denoted as jpx. which is the Bessel function of first kind, or Bessel function of first kind of order p, because it depends on p. So in y of x, I replace a naught by 1 by 2 raised to the power p factorial. P factorial will cancel out. Now one more observation here is that when I wrote y of x, recall the Frobenius series solution method, it is x raised to the power r, so, or x raised to the power m, so value of r is p, and then the series, so that's why it is x raised to the power 2n plus p. So now p factorial would cancel out, and once they cancel out, so this cancel out with p factorial, and 2 raised to the power p and 2 raised to the power 2n, so it becomes 2 raised to the power 2n plus p, or you can write it as x by 2 raised to the power 2n plus p. So this is your Bessel function of first kind. Please do remember it. Minus 1 raised to the power n by n factorial n plus p factorial, x by 2 raised to the power 2n plus p. Now the first question is, do you see this JPX is well defined? Well defined means that, does it hold for all p greater than 0? What do you think? For example, let's say I consider n is p is equal to 1 by 3. Then in the denominator, it would be the first term is 1 by 3 factorial, then 4 by 3 factorial, and so on. Is 1 by 3 factorial, 4 by 3 factorial well defined? Do you know the value of 1 by 3 factorial and so on? So this is the problem. If we consider p to be a positive integer, then there is no problem. But other than the integer, there may be problem. So to understand that is n plus p factorial is well defined for non-integer terms, we will introduce the concept of gamma function. So gamma n is defined as 0 to infinity e raised to the power minus x raised to the power n minus 1 dx, where n is strictly greater than 0. Yes. So if I have to compute gamma 1, it comes out to be 1. If I have to compute gamma n plus 1, then it can be written as limit b tends to infinity integration from 0 to b e raised to the power minus x raised to the power n dx. Yes. So to proceed further, I consider e raised to the power minus x as first function, x raised to the power n as second function, and now we will see that the second term is 0 to b x raised to the power n minus 1 e raised to the power minus x. So second term would give you n gamma n. Now in the first term, when you put limit x is equal to 0, it is 0. I just have to see what will happen when I put x is equal to b. Please find it by yourself also. When you put x is equal to b, then it becomes b raised to the power n by e raised to the power b. Now from here you are getting infinite by infinite form. So to apply L'Hopital rule, you keep differentiating it and keep applying the limit. When you differentiate it n times, the numerator it becomes n factorial, and denominator would remain e raised to the power b. In that case, when you apply limit b tends to infinity, it is b n factorial by infinity, that becomes 0. It means the first term is 0 and the second term is n gamma n, and I can write gamma n plus 1 is n gamma n. Clear? So this is the, if n is an integer, then you can easily observe n gamma n becomes n minus 1 gamma n minus 1 and so on n factorial. Yes. Now one important thing is gamma n is only defined when n is greater than 0. So what will happen if n is less than equal to 0? So let's see. Let's assume that n is from minus 1 to 0. If n is from minus 1 to 0, then n plus 1 is from 0 to 1. Yes. So n plus 1 is any number, yes, which is positive, which is greater than 0. It means the gamma function is defined for n plus 1. So if above equation you see the right hand side, gamma n plus 1 is defined when n is from minus 1 to 0, and the denominator n is well defined when n is from minus 1 to 0. It means the right hand side, the numerator and denominator, are well defined when n is from minus 1 to 0. And this is why your left hand side is also well defined. The only thing is, if n is from minus 1 to 0 and you need to compute gamma n, so you compute it by considering gamma n plus 1 by n. The definition would not work. Similarly, if it is from minus 2 to minus 1 n, then n plus 1 is minus 1 to 0. Again, gamma function is defined just above from minus 1 to 0. Therefore, gamma n plus 1 is defined from minus 1 to 0, and that's why gamma n would be defined from minus 2 to minus 1. Similarly, I can extend it that when n is negative and not an integer, then the gamma function is well defined. At the same time, when it is an integer, for example gamma n, and you consider n is tending to 0, then it is limit n tends to 0, gamma n plus 1 by n. Now gamma n plus 1 is gamma 1 and denominator is 0, so 1 by 0, which is infinite. It means gamma function is not defined at 0. Similarly, if you check for minus 1, so at minus 1 gamma n plus 1 divided by n, so n is not a problem, so I am just looking for gamma n plus 1. So limit n tends to minus 1 gamma n plus 1 is limit t tends to 0 gamma t, which is infinite from above, because limit n tends to 0, gamma n is infinite. It means for all the negative integer and 0, the gamma function is not defined. So from here you can observe that when n is greater than 0, gamma n is defined by the definition. When n is not an integer and n is less than 0, gamma n is defined as gamma n plus 1 by n. And when n is negative integer or 0, then it is not defined. It means that if you go back to jpx, then your jpx is summation minus 1 raised to the power n by n factorial n plus p factorial. So n plus p factorial, both n and p are greater than 0, and that's why I can write it as in the form of gamma n plus p plus 1, which makes sure that gamma n is defined, which shows that jpx is defined for all p greater than 0. Yes, now the other solution would be j minus px. I have to see what will happen, or is it well defined when we consider j minus px. So to consider j minus px, because the other root of the initial equation was minus p, I will consider two cases when p is not an integer. Yes, let's say p is 3 by 4. Then p and minus p, so 3 by 4 minus 3 by 4, they do not differ by an integer. It means there exists two Frobenius series solution. The only problem comes when p is 1 by 2, 3 by 2 and so on, because 1 by 2 minus 1 by 2 is 1, which is an integer. So there may be problem. They differ by an integer. In that case, there may exist one Frobenius series solution, or there may exist two Frobenius series solution. Okay. So I will discuss the case of p is equal to half 3 by 2 separately. But for the other values, when p is not an integer, surely m1, m2 do not differ by an integer, and there exists two Frobenius series solution. One solution is jpx, the other solution is j minus px, where j minus px, it is very easy observation. In jpx you replace p by minus p, you simply get j minus px. It means when p is not an integer and p is not equal to half 3 by 2 and so on, then y of x is c1 jpx plus c2 j minus px. Now what will happen when p is equal to half, 3 by 2 and so on? Let's see. So when p is equal to half, if I go back and try to compute, because a1 a3 I have not computed, so if I go back and try to compute a1 a3 for m is equal to minus p, then your equation was m plus 1 square minus p square a1 is equal to 0, and if I substitute m is equal to minus p, it becomes 2p minus 1 a1 is equal to 0. Now in this equation, if I substitute p is equal to half, then a1 is arbitrary. I cannot compute the value of a1. And when one of the coefficient is arbitrary, then there exists two Frobenius series solution. Similarly, when p is equal to 3 by 2, your a3 would be arbitrary and so on. It means in all these cases also there exist two Frobenius series solutions. Since a1, a3, a5 all are arbitrary, or like in the first case you get the solutions in terms of a1 as common and a3, a5 would be computed in terms of a1 only. In the other case, everything would be computed in terms of a3. So just for the convenience, I assume that all these a1, a3, a5 as 0. And in that case, because they are arbitrary, they can take any value. So I am assuming them to be 0. And if I assume them to be 0, then for all these values, p is equal to half, 3 by 2 and so on, my y of x would be c1 jpx plus c2 j minus px. It means what I need to remember is that if p is not an integer, then my y of x would always be c1 jpx plus c2 j minus px. Now let's see the other case when p is an integer. So let's assume p is equal to m, where m is greater than or equal to 0. In that case, my j minus m x would look like as follows, where you know that n is from 0 to infinity. Yes. Now interesting observation is that in the denominator I have minus m plus n factorial and n is starting from 0. Okay, so let's see that your m is 2 and n is 1. So it is minus 2 plus 1, which is minus 1 factorial. Minus 1 factorial is infinite, and therefore the whole term would become 0. So easy observation is 1 by minus m plus n factorial would be 0 when n is any value from 0, 1, m minus 1, since p is an integer or m is an integer. It means that this summation starts from m. So n is equal to m and so on. Now in this summation, if I want to start it from n is equal to 0, so what I can do, I can replace n by n plus m. It's easy observation. For example, when n is equal to m, the first term is minus 1 raised to the power m factorial, then 0 factorial. Same would happen here when you substitute, so minus 1 raised to n plus m and so on. So first term would match even all the things. This is very easy observation. But if you simplify it and take minus 1 raised to the power m common, then the remaining summation would be jmx. It means when m is an integer, then you got j minus mx as minus 1 raised to the power m jmx. It means they are linearly dependent. Yes, or by using this method, or I can say that when m is an integer, then jmx c1 jmx plus c2 j minus mx is not a general solution. So how do I get the general solution? I use this standard method y2 is equal to vy1, and I substitute the value, then you will observe that y2 comes out to be jm integration 1 by x jm square x dx. I cannot solve it further, so I will leave it here. It means what I need to remember is when m is not an integer, then the general solution is c1 jpx plus c2 j minus px. and when m is an integer, then it comes out to be c1 jmx plus c2 and then jm integration 1 by x jm square dx, which is very complicated. So in the chapter we will mainly focus on the cases when the general solution is c1 jpx plus c2 j minus px. This is a quick remark which is given in the book, that I am not going into the detail, we do not discuss it. That we found that the Bessel function of second kind, when p is an integer and p is not an integer, comes out to be different. If I have to define both the cases using one term, then I can say that ypx is jpx cos p pi minus j minus px sin p pi. Okay, if you want to see the detail, you can see in the book, but we are not discussing it. This is important observation, that if you see the first term of j minus px, then it is actually 1 by minus p factorial x by 2 raised to the power minus p, or I can write it as 2 by x raised to the power p. Now about x is equal to 0, it becomes, because p is positive, so it is not bounded, it goes to infinite when limit x tends to 0. And this is the first term. It means overall j minus p is unbounded near x is equal to 0. It means the bounded solution of the Bessel equation about x is equal to 0 is jpx. Very important remark. I will do an exercise based on this remark. Okay, so please do remember it. The third remark says that if I compute J0 and J1 and plot them using MATLAB, for example, then this is how the graph looks like, which means J0 and J1 vanishes alternatively and they have infinitely many zeros. Yes, we are not proving it, we are just observing it from the plots. Okay, so let's do the last or the very interesting exercise from this section. Find the general solution of this given differential equation. So if you simplify this differential equation, then it looks like x square y double dash plus xy dash plus 4x square minus 9 by 25y is equal to 0. Now recall what is Bessel equation. Does it look like a Bessel equation? So Bessel equation is x square y double dash plus xy dash plus x square minus p square y is equal to 0. So here instead of x square I have 4x square. So you can see this problem as follows in the exam, that transform the given equation into Bessel equation and find its general solution. Yes, so instead of x square I have 4x square, or instead of x I have 2x. So that's why what I can do is that let 2x is equal to 2t. That gives me y dash is equal to dy by dt and dt by dx. That gives you 2 dy by dt, because dt by dx is 2. And that means that d2y, this we did many times, is 4 d2y by dt square. Now rest is simple, you just substitute all the values into the equation 1. So x square is t square by 4, then you have 4 d2y by dt square plus t by 2 and 2 dy by dt. Please try it by yourself. Then t square minus 9 by 25y is equal to 0. Why there comes t square? Because 4x square is t square from here. So it easily gets reduced into the Bessel equation, which is t square d2y by dt square plus t dy by dt plus t square minus 9 by 25y is equal to 0, which is a Bessel equation, and therefore the general solution yt is c1 j3 by tp, because p is 3 by 5, plus c2, and it's not an integer, so that's why this is how my general solution looks like. If I have to find y of x, then I replace t by 2x. Okay, so that's all from today's class. In the next class, we will see many properties of Bessel functions. Thank you.